Welcome to Brain Vision.
Hello everyone, and in this video I'm going to be solving problem 58 from chapter 7 of the Sears and Zemansky's University Physics textbook. So the first thing I'm going to do is I'm going to read through the problem, make sure that we fully understand the problem and what the problem is asking of us and what the problem expects us to actually do. All right, so problem 58. A truck with mass M has a brake failure while going down an icy mountain road of constant downward slope angle alpha. And that's shown in figure P758. And that's the same figure that I have crudely drawn already on the screen. Initially, the truck is moving downhill at speed V0. After careening downhill a distance L with negligible friction, the truck driver steers the runaway vehicle onto a runaway truck ramp of constant upward slope angle beta. The truck ramp has a soft sand surface for which the coefficient of rolling friction is mu. What is the distance that the truck moves up the ramp before coming to a halt? And solved by energy methods. So it's a good thing the problem wants us to solve by energy methods, because we could solve this as if it were a chapter 5 problem where we draw a bunch of free body diagrams and use the kinematic equations of motion to keep track of the truck. However, we really don't want to do that just because the math is going to get very complicated. When we use energy methods, we only care about what's happening at two specific points. We care about what's happening at the beginning and we care about what's happening at the end point. So all we need to figure out is what is the total energy initially in the system and what is the total energy finally in the system. So the total energy that is in the system to begin with, I'm going to abbreviate that over on the left side when the truck is starting from, and I'm going to call that total initial energy EI. So that's the total energy that's going to be in the system in the first place. And then the total energy afterwards is going to be when the truck moves up the other side of the ramp. So I'm going to draw that at some point later. I'm going to have the truck over here, and that's going to have gone up the ramp at some point and it's going to come to a halt. So we want to know the distance the truck moves up that ramp. So we're going to have to label that, and the problem doesn't give us a variable to use, so I'm just going to use an X to show what distance the truck moves up the ramp. So that's the variable we're going to be solving for, is this value X, the distance the truck actually moves up the ramp. And once the truck moves up the ramp, then there's going to be some total energy, some total final energy in the system. And I'm going to denote that by EF for total final energy in the system. So now in a perfect world where energy is perfectly and completely conserved, these two amounts of energy should be completely equal to each other. So that means that the total initial energy should equal the total final energy. That is, of course, in a perfect world, what's happening. Total initial energy is equal to the total final energy. However, we're not in a perfect world in this case. We're in a world where there exists friction. So that means the force of friction is going to do some work on the truck as it moves up the hill, and that force of friction is going to take away some of the total initial energy in the system. So this total initial energy, then we have to subtract whatever work is done by friction. And then that's going to give us the total final energy that will be available. So some energy is lost in the form of heat due to friction, which is what we want in bringing the truck to a halt. So now the rest of solving this problem is just making the right substitutions into the problem. So the first thing is we need to break down our energy terms. So the total initial energy is composed of two things: the kinetic energy of the cart that's moving and the potential energy. And in this case, the only source of potential energy in the system is due to gravity. So we're going to have our gravitational potential energy. So we know from the textbook, we know what the kinetic energy terms are. And we know that the total initial kinetic energy, which I'm going to call Ki, that's the initial kinetic energy, is 1/2 times the mass of the truck that we're given, that is m, times the speed of the truck, which we're given as v0. So there's our basic definition for kinetic energy. And then we know that the total initial energy, I'm going to call that ui, that is just the gravitational potential energy. So that's going to be m times our acceleration due to gravity, g, times yi. And yi, what is the value for the height that the cart is above this ramp. So we go to the truck, and I'm just going to draw the height, and I'm going to call that yi is the total height. Now, we can use some basic trigonometry to substitute in what we're looking at for this height, yi. Well, that, if we remember our trigonometry SOHCAHTOA, the sine of alpha is equal to the opposite yi over the hypotenuse, which in this case is the length L that the cart has, or that the truck has moved down the ramp. So we can then easily write that yi is simply equal to L times the sine of alpha. So we have L times the sine of alpha. So that will put the potential energy term in terms of the quantities that were given, alpha and L. So we rewrite the potential energy then, making our substitution as m times g times L times the sine of alpha. All right, so that first step is complete. And then we need to think about what the kinetic energy and the potential energy terms are after the truck has gone up the ramp. Well, that final kinetic energy is just going to be equal to 0, because we say that the truck has come to a halt. We want to know how far it moves when it comes to a halt. So its speed is going to be 0, therefore its kinetic energy term must be 0. So then we want to know what the potential energy is at this point that it's gone up. Well, that potential energy, I'll call that UF. Oh, excuse me. Sorry about that. My tablet is messing up a little bit. All right, so we have the potential energy term. So UF is equal to m times g. I'm going to call this YF, and it's going to be the exact same thing that we just did for the initial potential energy term, where YF is the height the truck has gone up the incline. So I'm calling that one YF over here. And that's just the height that's gone up. And we're going to do the exact same thing again, where we have that final height YF. And basic trigonometry, once again, will give us that, in this case, the distance we've gone up is now x, as opposed to the other side where it was L. So now it's the distance x because that's the distance we're interested in, times the sine of beta. So this is just the basic trigonometry that we're using here. So times the sine of beta. So that will then give us another expression for the potential energy. And that potential energy term will be m times g, making our substitution now that is mg times x times the sine of beta. All right, and there's one more thing that we need to figure out, and that's going to be what is the work that will be done by friction on the system. So that work that's done by the force of friction, well, that's just our basic definition for work. That work is simply going to be what is the force of friction acting over some distance. So that's going to be the force of friction, which we're going to denote with F, times the total distance that the truck moves up the ramp. So that's going to be the force of friction multiplied by X. So we need to figure out, well, what is the force of friction? Well, the force of friction, if you remember, and I should actually put a little subscript F so that we know we're talking about the force of friction in this particular case. Well, we know that the force of friction is just the coefficient of friction, which we're given as mu, multiplied by the normal force. And the normal force is just the force of the surface of the ramp that is pushing up that counteracts gravity. So come over here to the diagram, and I'm going to diagram the normal force as going straight up. So it goes straight up through that. And it's just the component of gravity. So we would have seen this back in chapter 5, where we know that the normal force, Fn, is equal to m times g times the cosine of beta. So that's just so mg cosine beta, that's the weight that's pulling down in the direction that's perpendicular to the surface. So that gives us the normal force. So that gives us then the force of friction then as being mu times the normal force, which is m times g times the cosine of beta. So now we can put that in to figure out how much total work is done by the force of friction. We're just going to make that substitution. And we're going to have that the total work done is mu times mg times the cosine of beta. So that's our force of friction. Then, of course, that whole thing will be multiplied by the distance x. So we have our force times the distance x. All right, so now we can come over here, and knowing everything and all these pieces that we've established, now we can substitute this in, and then the problem is just algebra in solving. So our total initial energy that we have, the total initial energy is just the sum of the initial kinetic energy plus the initial potential energy minus the work that's done. And that's the total final energy, which will be the final kinetic energy plus the final potential energy. But we've already established what all of these terms are. We know that the initial kinetic energy is 1/2 mv naught squared. So we have 1/2 mv naught squared plus the initial potential energy, which is mg L times the sine of alpha, minus the work that's done, which is mu times mg times the cosine of beta times x. And we know that that whole term is equal to the final kinetic energy, which is 0, plus the final potential energy term, which is mg x times the sine of beta. All right, so now the rest of this is just algebra, because what we're interested in finding is we want to find the value for x. So I'm going to underline that here. So we have two spots where we have x. So we just need to solve this. So the rest of this is just algebra in solving. Well, the first thing we can notice is that the mass term for the truck is in all terms of the equation. So the mass nicely cancels out. So I'm going to cancel out the mass. It just divides out, so we don't even need to worry about it. So then I can rewrite the expression as simply being 1/2 v naught squared plus g times L sine of alpha. And I'm going to move the work term over to the other side since I want to isolate x by itself. So that's going to be mu. That's mu times g times the cosine of beta times x plus gx times the sine of beta. So now I can factor out x from these two terms on the right-hand side of the equation. So I end up then with 1/2 v naught squared. 1/2 v naught squared. So plus g times L times the sine of alpha. And then that is equal to, and just pulling out that x term, x times mu g cosine of beta plus g times the sine of beta. So now I just divide out the expression and I've solved for x. That will give us then the final answer for the distance x that the truck goes up the ramp. So our final answer, once we divide out by x, is we get x equals 1/2 v naught squared plus g times L. Oh, excuse me. Sorry about that. The tablet's acting up again. All right, where was I? Ah, yes. So g times L sine alpha, and then the whole thing divided by mu g cosine of beta plus g times the sine of beta. All right, and there we have it. And then that's our answer for how far it goes up. So now if this problem gave you numbers, which it didn't, but if it had numbers for the initial speed v0 and for the length L and for the angles alpha and beta, we would be able to then plug it in and then get a value for x. But we haven't been given any numbers. We're just working symbolically this whole time. So this is as far as we can go. You can, of course, manipulate this if you wanted to put it in a fancier form by like dividing out g from a bunch of the terms and making it a little simpler. But since we're working symbolically, we might as well just leave it as it is. So there's our final value for x that I've now circled. So the key to keep in mind is it may look confusing because there's a lot of algebra involved in just solving the equations, but the basic principle is we just started with energy conservation, figured out how much total energy there was in the system to begin with, and then we have to subtract away the energy that's removed due to work done by the force of friction, and then that gives us the total amount of energy. So the beauty of solving a problem like this with energy methods is we don't necessarily care what's happening to the truck in between the two states. We only care about the initial state and the final state for energy, as opposed to if you were using the kinematic equations of motion, such as if this were a chapter 4 and 5 problem, you would have to basically keep track of the truck at every single step along the way. Here we only need to know what's going on with the truck at two particular instances. So we've done that, and then the rest is just plugging everything in, and then it becomes just a matter of algebraically solving the equation. So hopefully that helps you if you are stuck on problem 58 from chapter 7. All right, have a good day.